Section 3.1, definition of the derivative. And what we will do in this section, I will introduce the derivative. We will start with the concept that we actually investigated in chapter 2, the slope of the tangent line. So let's just have a look really quick. Slope of the tangent line was, as we remember, the limiting position of the slopes of the secant line. So in the blue line, it's actually a secant line. It's point P, point Q, and this is the difference quotient. I don't have to explain. We all know what it is, rise over run, delta y over delta x. And we actually, the point is, we're looking for the slope of the pink line, the slope of the tangent line at the point A, f of A. We're strongly using the slope of the secant line. And what we want x to approach A. And that's mean we want that limiting position. That x coordinate must be arbitrarily close, almost at A, arbitrarily close to A, meaning that delta x will become almost zero, almost, because we cannot divide by zero. That means it is almost zero. And we remember this was defined as an instantaneous rate of change, slope of the tangent line. That means let's look at this. We're doing this limiting position beautifully. Point Q is approaching point P. And when this is extremely close, we may compute that limit, and then we will approximate by this slope of the tangent line. It means now slope of the tangent line is the limit of the slopes of the secant line. And I can put this as a nice limit definition. Let's see. One more time, tangent line to the curve f of x at the point A, f of A, is the line through the point P with the slope. And we can see difference quotient and the limiting position, x approaches A. Coordinate of the Q is getting really close to the coordinate of the x coordinate of the Q is getting really close to the x coordinate of point P, because that's what we have. And we also learned in chapter 2 that limits, whatever we will set up, we may have a situation that this limit is undefined. That means this is the slope if the limit exists. Okay? We will look at some cases, some weird cases and some standard cases. And that means this is the slope. We may compute, you master the limits if this limit exists. Okay, let's start. I think this was also our one of the first exercise in chapter 2. However, we didn't know the limit exactly. We used the calculator to approximate the value, but let's do it again through the limits. Find the equation of the tangent line to the parabola x squared at the point 1, 1. This means what we need? We may use point slope form. I have to, but okay, I will. Yeah, I have it. Point slope form. I can maybe write here point slope. That's the easiest form since the point is given, and then point is 1 and 1, 1. That's mean we have y1 and x1, but we will need slope. That means let's use the definition. Slope of the tangent line for this function is defined as a limit as x, the coordinate of q, is approaching 1, coordinate of p, and this is the quotient, the difference quotient. F of x minus f of 1, x minus 1. Now let's evaluate. F of x is x squared, f of 1 is 1 squared 1. And now we have a limit, easy limit. We remember it's indeterminate form, 0 over 0. We may factor out, we may cancel out that common 0, and now we can use the direct substitution. 1 plus 1, 2, okay? This is the slope, okay? That's slope of the tangent. I use the definition. Let's please know this definition. And now, yes, now I type this point slope form. So easy 2x minus 1. Do I have the graph? I don't have the graph. Okay. Our best friend, parabola x squared. And at the point 1, 1, I will draw a tangent line. So tangent line has the slope 2, and the line is 2x minus 1. But we use the point close to x, to 1. Okay, we did it. Nice. Standard question. Okay, example number, oh, no, let's wait. A couple of notes. We did find, yes, like for instance, this one, we did find the slope of the tangent line. But based on the definition of the tangent, meaning of the tangent line and the curve at the point of this, like the intersection, the connection, intersecting is not a good verb, but when we go really close, when we will zoom in, we know that they almost like indistinguishable. That means sometimes we may have a question, we may see that slope of the tangent line is the same like the slope of the curve at that point, of course, because like when we go further, the slope goes different way than the tangent. Then the curve goes different way than the tangent. Then the slopes are different. But at that point, they are almost the same. That's the reason that we can call slope of the tangent as a slope of the curve at that point. Yeah? And then we can see when we will zoom in 1, 1, 1, 1, 1, 1. Please notice the scale from 0 to 2, from half to 1.5, from 0.9 to 1.1. The curve becomes almost like a line, like a tangent line. Okay? Now, what we will do, we will look at this one more time, but we will get different form of that limit, different form of the slope of the tangent line. And it's a little bit easier to use later for some applications and for some other definitions. Difference quotient, f of x minus f of a, x minus a. But what we will do, because we would like to reserve like x, the variable, for the function, yes, because this is function f of x. That means I know that we name point q x f of x, but what we will do, we will keep a and f of a, because that's given, that's always given. If we need a tangent, we need a point. And we will call this distance, which is actually delta x, we will call h. That's, this will become h. H, just additional label, additional, it's not a variable, additional, like, yes. Additional thing. I don't want to say variable, just additional, yes, additional letter. Okay, that means if this is if this point is a, then that x can be replaced with the distance a plus h. That means this is a plus h. If x is a plus h, this is a plus h, then the value will be respectively f of a plus h. Right? That means it will be not f of x, will be f of a plus h. That means this is f of a plus h. Okay, and since we remember that distance, the point is this distance supposed to be tiny, small. Yeah, that means h is approaching 0. It's getting smaller and smaller in order to get the slope of the tangent line. Okay, that means what we will have, if I will replace this with a plus h, this is a, and x, I will say it's a plus h. A and a will cancel out and only h will stay. That means this is a new form, new formula for the slope of the secant line at the moment. But if I will add this notation, if I will say h approaches 0, that distance between the points P and Q is almost 0, then is the slope of the tangent line. Okay? I can even write limit as h goes to 0, f of a plus h. It's just the minus f of a, which we can see is that distance. It's still rise, delta y. And then over h is x, delta x. That means it's still the same thing. Yeah, it's still delta y over delta x. H is hidden here. Okay, yeah, that means this will be the slope of the tangent. Slope of tangent line. Okay, slope of the tangent line, different form. Let's keep moving. Oh, and now we can see I typed this. And let's look at the definition. That means this is the previous one from 5 minutes ago. F of x minus f of a, x minus a, having x. This one is without x. Because we will see it will be much easier to compute different things. That means this is also a definition of the tangent line. F of a plus h minus f of a over h, h0. Tangent line at a, at the point a, f of a. Okay? And now we can possibly take a function. Let's practice this. And let's find the equation of the tangent line to the hyperbola 3 over x at the point 3, 1. I think I have, that's the hyperbola, blue. Yeah, because this is function just 3 over x. And then in the hyperbola in the first and the third quadrant, and the tangent line at the point 1, 3. We have the equation. It's the different form, like a standard form. But let's get this. Let's get this equation. Okay. Let's get this equation. That's what we will do. We need a slope. We remember we will use point slope form, but let's find a slope. That means I'm using the new form. A plus h, which will be 3 plus h, because this is a, and this is actually f of a. You can see f of 3 plus h minus f of 3 over h. Okay, now let's evaluate. In order to find f of 3 plus h, I will take a function and replace x with 3 plus h. So we can see we have a function 3 over x. That means this will be replacing x with 3 plus h, and 3 f of 3 replacing x with 3. 3 over 3, 1. Okay, that's we have this limit. This is one more time, f of 3 plus h. We can see 3 over x, no x, 3 plus h. 3 over 3, it's 1, because this is f of 3. Okay, and we remember from chapter 2 again, how to deal with this limit. When we will do the direct substitution, it's 0 over 0, but we know we have to rewrite, find the common factor, cancel out, and use direct substitution. That's my first step will be, I will eliminate these fractions. Yeah, just algebra now. Too many fractions. This is the small denominator, and I will multiply each term, this term, and then 1, and then h by 3 plus h. Let's see what's happened. I can maybe see when we will distribute. When distributing this will be cancelled out. Only 3 will stay. And multiplying by -1, yeah, I will keep it for a second. In the parentheses, and I will distribute. And denominator, I will just keep the product. H times 3 plus h. Because we know we cannot distribute. That h is that 0. We would like to cancel out. That's the reason that we need a product form. Okay, let's distribute negative. Let's cancel out 3 minus 3. And now we see the common factor. H and h is gone. -1, h is 0. I mean direct substitution. -1/3. So we did find the slope of the tangent line through the limit definition. Yeah, this is the slope of the tangent, important, and it's that new definition, h. Yeah, this is slope of tangent. Okay. So now point slope form, of course, 3 and 1 and -1/3. And when we distribute and get the slope intercept form is -1/3 x plus 2. If you will multiply everything by -3, you can get that form also. Yeah? And put all of the terms on the right-hand side, on the left-hand side. Okay, slope of the tangent. Okay, now We remember also that the slope of the tangent line was like the instantaneous velocity. Slope of the secant line is just the average velocity, average rate of change, like displacement over the time. And this is displacement because now you may notice I am using this new form, the h form. I mean, when we will say distance over the time, that's the distance on the time interval, it's h. That means distance over the time. This represents the average velocity, average rate of change of the distance with respect to time. Okay, but the instantaneous velocity, I can define as a slope of the tangent line. In chapter, the beginning of chapter 2, we explain this more carefully. Then now I can say that this definition of the slope of the tangent is exactly the same like finding the instantaneous velocity. We can see the same limit. And now I would like to just say in general, if we would like to compute any instantaneous rate of change, the rate of change at that instant, anything what is changing in around us, some interest, some costs, some loss, some population, how the population is growing, how the viruses are spreading. Like if we want the change, we want rate the change, at that instant, we will always use that limit, always. This limit is really widely used. That means I do have, okay? That means this limit will always arrive when we would like to calculate the rate of change, not the average, because we know the rise over run like this is actually 0. It's theoretically it's almost 0 over 0, no changes, but actually it is because h is not exactly 0. And since this limit is so widely used, slope of the tangent, instantaneous velocity, or any instantaneous rate of change, we have a special name and special notation. And finally, the special name is the derivative. Derivative of the function f of x at the point at a. However, I can say the point a, f of a. Yes, at the point a. I mean, this is derivative. Finally, we do have a special also notation. Like we cannot really say f of a. We will say f prime. Prime means derivative. If you see this for the first time, and now everything makes sense. That means f prime of a, derivative of the function f at the point a, and it's defined like this. Yes, we know everything now. Okay, we know everything. It's still a long process to compute this. I mean, not extremely long, but it's a long process to compute. I promise we will get some shortcuts, but at the moment we have to master that limit definition. That means this is a definition of the derivative. Did I type this nicely? Yes. Yeah. The derivative of the function f at the number a, it's denoted by f prime at a, f prime of a, and it's defined like this: limit as h approaches 0, f of a plus h minus f of a over h. We may also say this. This is also that slope of the tangent, the older version, f of x minus f of a, and we can see x, the coordinate, the x coordinate of q is approaching the x coordinate of point P. As we can see, and that difference, yes, it will be 0 if they are almost the same, almost 0. I mean, this is also the definition, but we will probably focus on this one since it's a little bit easier and later it's a little bit less confusing. Okay, definition of the derivative. And let's find. Now I can use that terminology, compute f prime at 3 for the function x squared minus 8x. Okay? So we have to find the derivative of this function at the point 3. I can also say find the slope of the tangent to that parabola at 3. The same thing. Derivative is the slope of the tangent. Okay, I didn't type. Okay, good. Let's write it down. Derivative is defined as a limit as h goes to 0. And I will also recommend, maybe you can watch me now what I'm doing, and then you may get back with your video, pause the video, and do it again. Okay, please work on this. F of A plus H minus F of A over H. And A is 3. Okay, limit as H goes to 0. Difference quotient. F of 3 plus H minus F of 3 over H. Limit as H approaches 0. F of 3. That means I can maybe say F of 3 plus H. We do have a function F of X. It's X squared minus 8 times X. Now I will replace X with 3 plus H. X squared will be 3 plus H squared minus 8X, no X, 3 plus H. And we can see what I did. I just replace X with different input, 3 plus H. Okay, 3 plus H squared minus 8, 3 plus H. I mean, this is the first minus, and now we need F of 3. F of 3, I will replace X with 3. 3 squared minus 8 times 3. 9 minus 24, I think. It will be negative 15. Yes, okay. It will be negative 15. Let me put brackets and not 5. Negative 15. Okay. All over H. Let's expand this. Okay. 3 plus H squared. 9 plus 6H plus H squared minus 8 times 3, 24 minus 8H plus 15. Okay. 9 and negative 24 is negative 15 plus 15 gone. And then 6H, let's add the like terms. 6H, H squared maybe first, 6H minus 8H, negative 2H. And we can cancel out. Factor out first, factor out. And yes, the common 0 is gone. H minus 2, I can maybe write here, which I supposed to write underneath. That's how you can. And now H is direct substitution. The slope is negative 2. Okay, the slope is negative 2. And we may check if it's negative or the derivative. Function x squared minus 8x, when I factor out x, its parabola open up, and 0 and 8. 0 and 8 are the zeros, because we just need the zeros. And at point, where is the point? At 3, if we actually substitute 3, we will have negative 15. We know that. That means a little bit longer. It's okay. My scale is off, but labels are correct. And when we draw, that means a little bit longer because I didn't check exactly. And when we will draw a tangent, it will be, okay, that means it's definitely negative. It means slope is negative 2. We don't have to find the whole equation. That means this is, that's the, derivative is the slope of the tangent. Please make this connection in your mind. Then everything will be easier. Or like we also know, slope of the tangent is the same like slope of the curve. How this curve is changing at 3, negative 2. That means we will, the projection is that we will lose 2 items per minute. If depends on the units, depends on the scenario. Okay, make sure that you know how to get this negative 2 through the limit definition of the derivative. Okay, I have the work. You may also pause the video and look at this, the same thing. Okay, now I have another one, but what I will suggest that you will do it. Okay, pause the video, don't look at the solution, and then check the solution. And the solution is supposed to be, okay, I hope, okay, pause the video. Okay, work it out, and I hope now you are back. Let's see. You have that step, this one, this one, this one, this one, this one, and this. That means since number a is just a, just like a number from the domain, the derivative is in terms of a. If a is given, we can compute. And that means this is derivative. It's still, yes, I can still say is a slope of tangent. Derivative is the slope of the tangent line, yes, at point A, at A. Oh, we do not have A. Okay, that means 2A minus 8. Okay, and now what we can do, if we will have question like this, the part B, find the equation of the tangent line to the parabola, the same parabola, at the point 3, -6. So this is parabola. That's the point 3, -6, and it's -2x. Let's try to get it. You will always start with the point slope form, substituting point, and now slope. We know what is slope. Derivative. Derivative. Slope is derivative. And that derivative, I mean, okay, this is the derivative. I'm just here, my point was to copy from the previous page, and you also work it out, right? 2a minus 8, and now I can say that the point A, it's 3. That means I'm substituting 3. 2 times 3 minus 8 is -2, and now I am substituting. And yeah, when I distribute, this will be +6 and +6, they are cancelled out. This is tangent line. Tangent line. At the point 3, -6, we can see here, okay? But the point is to find the slope through the limit definition. Okay. That's lots of practice, please. Yeah, please practice. And now I have another one. Let's maybe quickly do it. Let's find the derivative of the function square root of x at the point 1, 1. And that means you will also write this. I didn't type it. Okay. Limit as h goes to 0, f of 1 plus h. I can put the a, right? F of 1, because this is a. Over h, okay? Limit as h goes to 0, f of 1 plus h will be square root, and instead of x, we will put 1 plus h. Square root of 1 is 1. Okay. And we recognize direct substitution is showing us 0 over 0. In order to simplify the root expression, we will multiply and divide by the conjugate. Square root plus 1 and square root plus 1. And in order to simplify, I mean, we will distribute everything in the numerator, but denominator, I will copy the, wrong. I will copy exactly, I can even use the same color. I will not distribute because we remember we need that product. When I distribute the numerator, it's like a conjugate, a minus b, a plus b. Multiplying this really quickly, we will square the first quantity, square the second, and minus. Okay, squaring the square root is 1 plus h. Squaring 1 is 1. Okay, only h stays. Perfect, that's what we're looking for. And let's actually see what is. We may cancel out, h goes to 0, and we will just end up with 1. Maybe write one more time, 1 plus h square root plus 1. When h is 0, square root of 1 is 1, 1 plus 1 is 2, 1/2. Okay, I mean 1/2, if we get the, like a graphical explanation, function square root of x is this. We know the function, the fundamental functions. 1, 1 is somewhere here. And yes, the slope is 1/2, makes sense, because we may, slope is 1/2. It's not that steep, my scale is even, okay, this time. Okay, please, yeah, please practice this way. Yeah, it's mainly the first step is algebra. I mean, the first step is calculus, the rest of them is algebra. Okay, then I have another one. but I will leave it for you. I don't have the solution. I will add the solution. I have another one, function and the point, find the derivative, and think that this is the slope of the tangent. And now let's look at this one. This one is easy. I can, yes, but we will have some, yeah. Find the derivative of the function 5 at a. Okay, at a. Theoretically, yeah, any point. You may think right away, this is constant function. Constant function. What is the slope of the constant line? It's just 0. That means this will be the conclusion of this example. Derivative of any constant function at any point is always 0. That means, let's see. This is a definition. A, yeah, if I will, the value, yes, we can see value that, I mean, function doesn't even depend on x. I don't even have to replace, because the value for any point, yes, if we have a constant function, value for any point, I can draw it like this is function 5. Yeah, that means value for 1 is 5, value for 2 is 5, value for 3 is 5, value for a is 5, value for a plus h is 5. Any point on the number line, on the x, will give us the value 5. Okay, that's the reason that I have 5 and 5, 5 minus 5. 5 minus 5 is 0, 0 over h. Yeah, h is a tiny number, it's not exactly 0. That means algebraically, this is 0. Okay, and now I just type for you the general, any constant function, b minus b, 0, 0. That means this is the conclusion. Please remember, derivative of the constant function is 0, and you don't have to go through the limit definition. I was just proving this, but that's for us. That's the proof, but this is, yeah, the conclusion, and we will use it. Constant function, doesn't matter what it is. What's the value is always the derivative is 0, because slope of that line is 0. And tangent to the line is the same line. Okay, now let's look at this function. Find the derivative at a, okay, at a, for the function 5x plus 1. You may also think, you probably know the answer. 5x plus 1 is the linear function, line. What is the slope of 5x plus 1? It is 5. I know that I can't hear you, but I can feel it that you answer 5. It's the slope, and that's the derivative. We don't have to do anything. But later, let's look at this. This is the derivative, f of a plus h minus f of a. Now we do have x. That means I can substitute instead of x, a plus h, and then instead of x, a. And I distribute the negative. Now I distribute 5a, 5h plus 1 minus 5a minus 1. We may see lots of items are cancelling out. 5h over h, it is 5. Yes, we knew it. We knew it. That means derivative at any point from the domain, but domain, all of the numbers, is 5. Yes, because slope of this line will always stay 5. And then I type general, mx plus, actually I can even say b, any number, mx plus b. Where am I? Mx plus, let's say b, that will be more general, even more general. Okay, and then I will, but everything gets cancelled out. This is cancelled out, this is cancelled out, m stays. That means derivative, yes, at any point from the domain, it's always a slope. That means, please remember, if we have line, don't think about any formulas, and even the limit definition, we have the proof, but this is derivative. Derivative of the line is its slope, m. Okay, and now I have this question. Okay, now I have this question. Let's try to answer. Okay, f of x equals to absolute value of x, and we have the question if this function has the derivative, if this function is differentiable at 0. That's another way to saying that function has the derivative. Yeah, we can see a little bit weird shape at 0, because based on the definition, we can check if this is absolute value of x. For the positive x's, absolute value of positive number is just positive, it's just x, but always if x is positive. If x is negative, absolute value of that quantity will be negative, then I have to make it positive. We remember this. And now we may use what is the derivative actually at any point in the domain, not including 0. I'm not, just any numbers. And since that line is x, that line is negative x, slope of the x is 1. Slope of negative x is -1. But this is only for positive x's, this is for negative x's. As we can see, we figure out everything except 0. Yeah, that's one more time, please think about slope derivative of the linear function as a slope. Yeah, please do not think about any formulas, which we still don't know the formulas. Okay, but now the question is, what is derivative at 0? Let's set up. Now we have to be careful because that 0 is the a value, and this is h is approaching small number. The distance is small. Okay, f of 0 plus h minus f of 0 over h. This means what we will get. Let's say if this limit exists. Our function is absolute value of x. Instead of x, I will put 0 plus h. And instead of x, I will put 0. Of course, looks funny. But this will stay absolute value of h minus 0 over h. Okay. Now, I think we have to split this in order to, we will compute h goes to 0 from the left-hand side. Let's say right-hand side, then everything is positive. I can replace absolute value of h just with h, and this limit is 1. And I can also find a limit as that h approaches 0 from the right-hand side, left-hand side. Then it's negative, that h is negative, I have to make it positive, and this is -1. That's when we may say this limit is undefined, because one-sided limits are different. If this limit is undefined, derivative is undefined. Derivative is undefined, we have no slope. Yeah, I mean no tangent, no slope. That means no tangent, no slope, no derivative. Or the other way, actually, no derivative, no slope, no tangent. The main really big conclusion, okay, the really big conclusion for this exercise is when we will see these sharp corners, sharp turns, like corners, kinks, cusps, function is not differentiable. Function doesn't have derivative or doesn't have a tangent. Yeah, like how can I draw this is tangent, oh, this is tangent. No, we're not even gonna try. No tangent at the corner, no tangent, no slope, no derivative. And we prove this. Okay, that means function doesn't have derivative. It's not differentiable at 0. Okay, and one more exercise for this session. Yeah, we have this. Another function. Is this function, cube root of x, differentiable at 0? Yeah. We may notice that function cube root of x is actually an inverse function, yeah, if that's easier, inverse function of x cube. Yeah, this is x cube, it's an inverse function. And if we remember, that function has at 0 horizontal tangent. Horizontal tangent. Okay, since this is inverse, this function will have vertical tangent. Let me write a little bit nicer, vertical tangent. And now I have to ask all of my students, I know we're connecting, I know that you're watching, even if we're watching at different times, we're making this connection that everybody's watching this session. Vertical tangent, what is the slope of vertical lines? No slope, that means no slope, no derivative, we know the answer. Function is not differentiable at 0. Vertical tangent has no slope, but let's prove it. That limit's supposed to be like undefined. That means, let's see. Differentiable means derivative, if the derivative exists. Derivative at 0 is defined as a limit, as h goes to 0, f of 0 plus h minus f of 0. Okay, limit as h goes to 0. Function is this. That means I will put 0 plus h to the power of 1/3 and 0 to 1/3. I know that you can skip these funny numbers. H goes to 0. Again, that 0 is different than this one. Okay, this will be just h to the 1/3. Oh, that's 0. We don't even have to write this. 0 over h. We may combine this because this is h to the power of 1/3 divided by h to the power of 1. 1/3 minus 1 is negative 2/3. I will rewrite without the negative. Okay, and now we can see it's 1 over 0, 1 over small number. 1 over small number is a big number. We will have positive or negative infinity, because if 0, yes, if is from the left or from the right hand side, if 0 is from the right hand side, will be positive. Yeah, I can just say this, right hand side. If it's the left hand side, will be negative. 1 over small negative will be negative infinity. As we can see, the limit is undefined. We knew it that something is not right. We do have these infinities. That means vertical tangent, we prove it, has no slope. Derivative is undefined, then no slope. No derivative, no slope, no tangent. However, we do have a tangent. In this situation, but we do not have a slope because it's a vertical tangent. Okay, enjoy these 12 examples and watch for the second session. I will carry on with the examples in this presentation. Thank you for now. Please rewatch even a couple of times. Enjoy your definition of the derivative. Thank you.